Thanks a lot for having me. I'd like to thank Professor Sugiyama and Dr. Chai for inviting me over here. I mean, having an opportunity to give a talk at TrustML seminar personally means a lot to me because when I was a PhD student, I somehow sneaked into this seminar and attended several of them and asked questions and learned a lot. And yeah, it's a really great honor to be here. And yeah, so today I'm gonna talk about the connection between statistical machine learning and reinforcement learning, which I've been investigating over last year since I joined Korea Institute for Advanced Studies. So today's talk will consist of two parts. And the first part is actually chronologically done later, but I think it's more beneficial to cover it first. So I'll first introduce value gradient sampler, which is sequential decision-making interpretation of sampling problems. So in this first part of the talk, I'll mostly focus on the sampling problem. The sampling problem is a problem of drawing samples, drawing independent samples, given a quantity called energy. So this energy, E, is a scalar function which defines a target density Q of X. Since there is, and the relation between energy and the target density is given in the given through this exponential form, and since this energy only specifies the target density up to the normalization constant, it's not a trivial problem to draw samples. There are a lot of applications of this. You can encounter the sampling problem in many application scenarios of machine learning and scientific computing. Probably one of the example is molecular dynamics simulation of computational chemistry. So in chemistry, there is multiple energy functions that defines the stability of configuration of a molecule, and with that, with those energy functions, you will get this landscape of energy, and the molecule will spend more time in a lower energy configuration and spend less time in a high energy configuration. So you will, or computational chemists usually want to sample a stable molecular configuration more often rather than unstable configurations. Yeah. So the most standard way of solving the sampling problem is a technique called Markov chain Monte Carlo, or MCMC. One of the, I think, most widely used example of Markov chain Monte Carlo is long-term Monte Carlo sampling. So this is a technique to draw a sample from a unnormalized distribution from the target density where you only know the energy. So you start from some some noise distribution, and then you iteratively update the particle using the Langevin dynamics, which guide this particle through the which drift this particle through the negative gradient of energy, and also diffusing this particle with some random noise. So after, so the promise of Markov chain Monte Carlo is that if you do this for very long time, your particles will converge to your particles can be considered as a random samples from the target density, which is defined by the energy. But however, the promise here only makes sense when you run it for very, very long time. So personally, I spend a large number of days and nights tuning this Markov chain Monte Carlo when I was doing my PhD. So I want to build something more reliable and faster. So instead of instead of just following the Markov chain Monte Carlo, we can try to think of training a parametric sampler. So instead of directly drifting the particle along the gradient of energy, you can try to find a more optimal or more effective direction of drift by training a neural network. So here I call this form of sampler a Langevin-like parametric sampler or parametric Langevin sampler. So here, if we figure out which drift direction, f theta, is more optimal to draw a sample in a finite number of time steps, large T, we can probably draw better samples in a shorter time steps. And if you think of this problem, finding the optimal drift direction, this can be interpreted as a sequential decision-making problem. So this whole problem now boils down to learning a parametric sampler, pi of phi. And we want to train this parametric sampler to be as close as to the target density Q of X. If we are able to do this, we can generate a sample. We can generate samples faster, of course, at the expense of training time. And arguably, this type of sampler can be more efficient and effective because the parameters are actually tuned towards the target density that we want to sample from. And of course, since this is a parametric model, we can reuse this parametric sampler to draw sample in future times. Oh yeah, sure. Oh yeah, feel free to interrupt during the talk.
Can you explain what is the difference between your method and the learned optimizers?
Learned optimizers.
Like optimizer which learn for fast convergence, or I mean it's parameterized and it can generalize to other models.
Yeah, I'm not sure if I understood the question correctly, but so since we are talking about the sampling problem, it's of course definitely closely related to optimizers, but it's not exactly the optimizer. So here, what we want to do is generate independent samples, not only finding the optimum. So, but in a sense that it'll be closely related to learn the optimizer. But here we want to try to build a learned sampler. Okay. Yeah, thanks for the question. So yeah, so one very natural objective function to use this natural objective function to train this parametric sampler is KL divergence. And if you write the KL divergence between pi and q in this order, this is particularly more natural because we don't need samples from target density to evaluate this. And if you look closely to this KL divergence, this can be interpreted as a maximum entropy reinforcement learning. Because as I said before, this policy pi is a sampler can be interpreted as a policy in sequential decision-making problem. And if you look into the expression, the log of target density Q can be considered as a reward. And this, or equivalently, this negative log Q is a cost. And there is a maximum entropy regularization in the end. So Yeah, what I want to say here is that this training of parametric sampler towards the target density is essentially a maximum entropy reinforcement learning problem. So before presenting like my proposal, I would like to mention that there are some like existing techniques that can fit into this framework. So for example, you're already familiar with this diffusion model, and diffusion model is also considered as a particular instance of this type of sampler. However, in diffusion model, the drift direction is determined by the score function of a diffuse data distribution. Well, here, so I would say that a diffusion model also belongs to this parametric Langevin-like samplers, but here in our problem setting, we don't have access to data points from the target density. So we cannot directly evaluate or compute the score function of diffuse data distribution. Also, there are a lot of recently there are several attempts to build stochastic differential equation based samplers, which also aim to build this adaptive samplers. Well, I would say there's a but then this stochastic differential equation based samplers are usually formulated in continuous time. So as you can see, in order to simulate this stochastic differential equation, you usually require a large number of time steps. So here, instead of requiring the full simulation of stochastic differential equation, I want to build a discrete time version of samplers that require significantly less number of time steps. So what I end up presenting is something called value gradient sampling. So based on the connection between this reinforcement learning and sampling problem, I leverage the idea that in reinforcement learning, the optimal action is the gradient of optimal action is actually along the gradient of value function. So at a high level, we train a value function that guides, we train a value function of our sampler, and then take the gradient of the value function to guide our drift in Langevin-like sampling. So I will dig deeper into, I will elaborate. So this value function plays a central role in reinforcement learning. So in general, the value function evaluates a value of a state, like how good a state is. So for example, in a game of Go, your value function will typically evaluate whether this state is going to win or you have very small chance of winning. So mathematically, this value function is defined as the expected cost from the current state xt. And if you learn this value function, your optimal action is simply the action that minimizes this value function. So here I use the cost formulation because we are in an energy minimization framework. But if you are using reward, you will use argmax. So let's get back to our original problem. So we want to train a parametric sampler pi of x, which minimizes the KL divergence between pi and q. The q is target distribution. We want to solve this problem by figuring out what is the optimal drift direction. And in order to solve this problem, there are two difficulties. So, I mean, so minimizing this scale divergence is not trivial actually for our Langevin sampling. So first, this entropy term, log pi, we cannot evaluate this term analytically. The second, if our sampler, since our sampler consists of multiple time steps, we cannot, we have to backpropagation through time, but this usually requires a large number of large memory overhead, and even if we have large number of even if we have sufficient memory, this will typically result in like gradient vanishing or gradient explosion. So I would suggest that value function is a natural solution to solving this, overcoming these difficulties in performing this mixed RL for parametric Langevin sampling. So in order to mitigate these difficulties, I would like to introduce some mathematical steps to obtain the objective function. So first, we apply data processing inequality to the objective function. To the KL divergence. So data processing inequality states that if you add new random variables to KL divergence, your KL divergence will always increase or stays the same. So the first line is the original objective function we want to address. And we add a new random variables from which we add the intermediate steps of Langevin samplers as a new random variable. So the pi x of t now becomes pi of x from 0 to t. And in order to do this, we also need to introduce some additional distribution on the right-hand side, the q tilde. And since data processing inequality holds regardless of the choice of q tilde, we will simply choose this q tilde as Gaussian. And instead of minimizing the original objective function, we try to minimize the right-hand side, which is obtained by data processing inequality. So this q tilde is some just random choice for data processing inequality. For the sake of convenience, we just set it to be Gaussian, but later we'll see that this actually has some meaning, and this leads us to some connection to the diffusion models. So after plugging all these expressions, the data processing inequality leads to an optimal control problem. So this objective function contains the terminal cost, the energy of the target density as a terminal cost, and the intermediate cost stems from each transition of Langevin sampler and the yellow term from q tilde as an intermediate cost. So, and if you look this is actually an instance of the classical optimal control problem. So we can apply the techniques that developed for optimal control problem to solve this, which is value-based dynamic programming. So here we can define the value function of this optimal control problem. Here, this is essentially the same expression from the previous slide, but the summation starts from t instead of 0. And we will parameterize this value function using a neural network, especially time-conditioned neural network. And this value function can be trained using temporal difference. Oh, actually, like this value function can be trained with any reinforcement learning techniques. But here we choose to train it with temporal difference learning, which is one of the most standard approach in reinforcement learning. So basically, we train this value function to regress its one step ahead value function. And this in that process, there's this running cost is involved. So after learning this value function, we can derive the optimal policy given the value function, which is defined as a gradient of value function. So this suggests that if we drift our samples along the negative gradient of value functions, we will be able to minimize the we will be able to solve this optimal control problem, which means that we will at least indirectly minimize the KL divergence we want to minimize in the beginning. So so here are some examples. So on the right-hand side, there's a target density that we want to generate samples from. And we learn our value functions, which results in which shows some diffused form of energy. And if we drift our samples along the negative gradient of value functions, our samples will gradually shift it towards the energy function that we want to sample from. And this is another example from like 9 Gaussians. So yeah, as you may have noticed already, we can actually derive what an optimal value function should look like. So an optimal value function actually should be equal to the energy of the marginal distribution of Q tilde. So Q tilde is the Gaussian distribution that we introduced in order to apply data processing inequality. So in the end, this Q tilde actually works like something like the forward process in diffusion model. So like this Q tilde actually defines how the target density is diffused along the time, and our value function should look like should be capturing this the energy, so negative log of this diffuse density Q tilde. So let me summarize the whole process. So in value gradient sampling, we first specified that auxiliary distribution, which serves as a diffusion process, and we train the value function. And after training the value function, we generate samples where in each step, we drift our samples along the negative gradient of value functions. So, so why am I advocating this value gradient sampling? So value models, so here we define value function instead of parameterizing the drift direction directly, like in score-based models. So what I'm saying is that these value models may be smaller or easier to implement than score-based models. And yeah, and as I said earlier, this value gradient sampler is trained this value gradient sampler is built in a discrete time steps instead of continuous times in stochastic differentiation based samplers. So it can be faster. And since this value gradient sampler is based on like the reinforcement learning framework. I would say that all the advanced reinforcement learning techniques that is built to train the value function more efficiently, more effectively, can also be applied to this framework. Well, this is a work in progress, so I'm hoping to get some more interesting experiments or more larger scale experiments pretty soon. But I will say that currently the results are promising, as I showed you earlier. And I think this is a really interesting direction to pursue. Yes.
So maybe I missed something. I'm not sure I understood. But compared to the energy function, or like the normalized log density that you have access to, you can access to the gradient of the energy function. Why would the value function learned by neural network? How can a value function be better than this energy function? Like, isn't the energy function the optimal in some sense, or?
Yes, that's a really great question, and that's what long-term Monte Carlo does. Yeah. But well, I don't know if it suffices, but maybe one example is that your energy function may have some local minima, and your gradient, if you like myopically following the gradient at each step, you might end up like reaching the local optima and not able to get out of it. But then if you like this, since this value function is has some like this look ahead behavior, you may have like different drift direction, so which leads you to leads you out of that local optima. Yeah. Thanks for questions.
But do we really have any noise ending term really helps
like in Langevin Monte Carlo?
Yeah.
Yes, you're also correct. But then all like this Langevin Monte Carlo, like the promise of Langevin Monte Carlo is that you run it like very long time, right? So like your added noise may not be sufficient to move up, take you out of this local optima. But if you run it very long time, you will at some point have large noise because like noise is random, and then you can come out. So it requires a lot of like time steps to simulate those behaviors.
But then if we assume that Langevin really covers the posterior, I mean, like global, not global, I mean, gold standard, then how you can assure your optimizer, I mean, your V can be make it really converged posterior, because it gives some different behavior.
Could you elaborate a little bit more?
Like if you assume Langevin as gold standard, I mean the truth, then how you can assure your sampler will converge to that gold standard? If your V is act different from Langevin.
I see. Yeah, I will agree that Langevin Monte Carlo is gold standard, given that if you run it an infinite amount of time. So I think, but here we want to optimize our sampler to generate good enough samples in the finite number of time step large T by minimizing the KL divergence. It is actually true that this KL divergence may not be zero, but we are like empirically saying that it's good enough given that it generates samples in a relatively smaller number of time steps. So maybe to your question, so it may not be identical to what Langevin Monte Carlo gives us in the infinite number of times, but we are empirically saying that it's good enough.
One more question. In long-term dynamics or something like MCMC method can learn some, sample some, can sample from postal distribution for neural networks, Bayesian neural networks. And is this method also can do some large-scale experiments, such like Bayesian neural network postal sampling?
Oh yeah, that's a really interesting question. Yeah, to be honest, we haven't done it, but it can be. In principle, it should be able to do it, but in order to do that, we need to train a value function in the space of weights, and that sounds a little bit compelling. Not sure if I can do that, to be honest.
Thank you.
Yeah. Right. Yeah, let me move to the second part of the talk. The second part of the talk is about maximum entropy inverse RL of diffusion models with energy-based models. So this work has been presented in UNIVS 2024 as an oral presentation. And yeah, this corresponds to the second part of today's title, like generative modeling is imitation learning. So in this work, we want to disseminate the idea that generative modeling is indeed imitation learning. And yeah, the reason why we advocate this view is that, yeah, so generative modeling is about generating samples that resembles the training data. And this process has a one-to-one correspondence to imitation learning. If you interpret the training data as expert demonstration and generate samples as your action, and the generative model itself, like pi of x, as a student policy. In this work, we want to leverage this connection to address challenges in generative modeling. So mainly we address two challenges in generative modeling. So first challenge is to train a short-run diffusion models. So diffusion models are diffusion models can generate very high-quality samples, but it usually requires large number of computing steps. And there is a huge practical interest in reducing the number of time steps. But if we do it naively, we will get very bad quality samples. And the second challenge is that we want to train an energy-based models without Markov-tree Monte Carlo. So this energy-based model is a very interesting class of generative models, but training of it requires approximations such as MCMC because of the normalization constant in its expression. So particularly, we want to embrace the idea of maximum entropy inverse reinforcement learning to address these challenges simultaneously. So this work has mainly two algorithmic contributions. So first algorithm is called diffusion by maximum entropy inverse RL, D by me. This is a joint training algorithm for a diffusion model and an energy-based model. And as a subroutine of D by me, we also propose diffusion by dynamic programming, which is a value-based reinforcement learning for diffusion models. Actually, this D by DP is it shares a lot of components with the value gradient sampler that I presented earlier. So yeah, let's start with diffusion model. A diffusion model, as I said earlier, can be seen as an instance of Langevin-like sampler. So we start from a noise distribution x0, and we drift and diffuse multiple times to get the final sample x of t. I will write the distribution of x of t as pi x. So this diffusion model can be interpreted as a behavior cloning algorithm, which is a very one of the most popular imitation learning algorithm. So this diffusion model is trained. So in diffusion modeling, we first construct a diffusion trajectory by repetitively adding noise to training data. And this diffusion model is trained to follow this diffusion trajectory step by step. So this diffusion trajectory serves as an expert trajectory demo. And this gives a diffusion model a very fine-grained training signal. And I believe that's one of the core component in the success of diffusion models. However, I believe behavior cloning is also responsible for the failure modes of diffusion models. So let's say, since diffusion models are usually trained with number of time steps of 1,000, if we train a diffusion model to follow the expert trajectory in 1,000 steps, and then we reduce the number of time steps to 4, we will get very blurry samples. This is due to the well-known failure mode of behavior cloning, which is a vulnerability under distribution shift. So if here the number of time steps is changed from what is given the training step, the noise will accumulate, like the error will accumulate from the beginning of the trajectory, and this will lead to student policy being very far from the training data distribution at the end. So in order to overcome this distribution shift problem in behavior cloning, we try to take inverse reinforcement learning approach instead. So in inverse reinforcement learning, so if we apply inverse reinforcement learning approach to this problem, we would like to first model the expert goal distribution. So it's not very well shown here, but there's a circle over there. We first model expert goal distribution, and then we optimize our policy directly to reach the goal. So by doing this, we can deviate from, we are free to deviate from the expert trajectory, but reach the same goal as expert did. So let's get a little bit more technical. So since the goal in generative modeling is training data, the distribution of goal is basically the training data distribution P of X. And we want to make our diffusion model to be close to the goal distribution P of X. And this now becomes another maximum entropy reinforcement learning problem if we write the KL divergence in this order. So here, the log P, like log likelihood of data is, that serves as a reward, but we don't know log P. And we often only know the training data. So we have to estimate log P from data. Since we are not interested in the absolute value of P, but we are interested in log P, energy-based model is a very natural choice for a surrogate model for P. So we fit energy-based model to the data distribution P of X using maximum likelihood estimation, which leads us to the KL divergence, which is written here. So we can learn energy-based model first, and then as a reward model, and use that energy-based model to train our diffusion model as a policy. So if you are familiar with the RLHF and how ChatGPT is trained, this is essentially a pipeline of RLHF. So you first learn the reward and then use the reward to train your policy. We can do it in a simultaneous, we can do it in a step-by-step manner, like as written here. But the training of an energy-based model is usually very difficult for, I mean, it's feasible, but difficult because of the normalization constant. So we have to introduce approximations such as MCMC. So in this paper, we propose an alternative approach where we want to train the reward and policy simultaneously. In order to do that, we convert the previous problems into a single minimax problem. So here, this objective function is called generalized contrastive divergence, which consists of the difference between the two KL divergences introduced before. This might look a little bit confusing, like a little bit complicated, but if you look closely, it's not that complicated. So if you look into pi, is basically you want to make your pi diffusion model to be close, to become closer to energy-based model Q, and this energy-based model Q want to be closer to data distribution P of X, while trying to move away from the diffusion model pi of X. So by using this contrastive term, like by using the difference of this KL divergence, the normalization constant is canceled out, so we don't have to compute the normalization constant. And this minimax problem can be shown to have a Nash equilibrium where all three distributions are the same. And yeah, and this is not completely new. So this objective function can be shown to be equivalent to other known objective functions in energy-based models. So to graphically summarize, this proposed framework, diffusion by maximum entropy inverse RL, trains diffusion models using energy-based model as a reward, and this energy-based model, which is a reward model, is trained in a contrastive manner by minimizing the energy of real data while increasing the energy of the generated samples from diffusion models. So if we write in an algorithmic form, for each mini batch, we sample real data and also we generate samples from diffusion models and update the energy-based models in a contrastive manner, and then use the energy-based model to train the diffusion model. Well, as I said in the first part of the talk, this minimization of KL divergence, like a KL divergence between diffusion model and energy-based model, is also not trivial, and this can be addressed by very, very similar mathematical techniques that I presented in the first part of the talk. So it'll be, so yeah. So if we want to train our diffusion models to minimize this KL divergence, we will have the same set of difficulties that I presented in the value gradient sampling. So we cannot compute the entropy directly, And if we want to do backpropagation through time, we will require a large memory. So yes. As we did in value gradient sampling, we can avoid the difficulties by introducing an upper bound and also by introducing value functions. And all the mathematical equipment will be like highly similar. So we will introduce, we will use data processing equality to obtain the upper bound, and the obtained upper bound will have a form of optimal control problem. And in order to solve this optimal control problem, we will use value functions. And this value function is again trained by temporal difference learning. But this time, instead of directly computing the gradient of value function, we want our diffusion model to be optimized using this value function. So also graphically summarize, to also graphically summarize. So instead of backpropagating through the whole diffusion model, we train a value function that encodes the information. We train a value function to guide the earlier steps of diffusion models. And this technique is what we call diffusion by dynamic programming. So basically, this is an application of classical value-based dynamic programming to train a diffusion model with respect to the reward. So in the end, the whole framework, the d by dp with d by me with d by dp consists of learning 3 components. So we learn energy-based model as a reward, and we also learn value functions and using the value function to update the policy diffusion models. It might look a little bit complicated. I would say that this is not particularly more complicated than the standard deep reinforcement learning implementations. And we, in practice, we also use a shared network for reward and values. So in the end, there is only like 2, the diffusion model and reward model, only 2 networks are trained. So, yeah, when applied to image generation tasks, so we were able to train a very high quality image generator, which generates samples in 10 time steps. And the quantitative results are also competitive. So our method can reach the same level of image quality as the full length diffusion models. And in larger image generation benchmarks, like the D by me also is capable of generating high quality samples by doing a favorable trade-off between the number of time steps and image quality. So yeah, I want to emphasize that maximum entropy regularization plays a crucial role in the proposed framework. So the temperature parameter in our framework governs the strength of the maximum entropy regularization. And if we assign like the right amount of temperature parameter, we were able to train a high quality generator, like high quality diffusion model, as well as an energy-based model which captures the true energy. However, if we remove the maximum entropy regularization, as you can see, the learned energy function will become nowhere close to the real energy of the data. So this maximum entropy regularization is a crucial component especially in learning the correct energy. So since this energy function captures the distribution of the data, this can also be applied for, can be used for performing anomaly detection. So basically, if energy is too high for a certain sample, it can be considered as an anomaly or outlier. So we applied this model to this learned energy function to anomaly detection tests, and we obtained quite competitive results. I know that there is huge interest in building a single step generator from a diffusion model, but unfortunately, I have to say that the proposed framework is not applicable to single step generation. Because the proposed framework is based on the value function, but then there is no value function can be defined for single step generation case. But however, I do believe that there's still some benefit of multi-step generation. For example, better guidance, or for example, in solving inverse problems. But yeah, for now, the proposed framework is not applicable to single step generation. So I would like to share some personal remarks from doing this work and the earlier work. So I want to say that many machine learning problems can be understood from this imitation learning perspective, because in the end, you want to make your machine learning model to mimic certain desirable behavior. So in that sense, many of machine learning problems can be understood from imitation learning perspective. And also, since many modern machine learning problems involves multiple steps of computations, many of them can be viewed from sequential decision-making problem. So I would like to say that, so like the works that I presented today are, at this point, I hope I have convinced you of these two perspectives by presenting the algorithms that I talked earlier. And I believe that this direction will lead us to like reach development of new classes of algorithms. Yeah, thanks for listening and thanks for your attention.
So is there any question?
Thank you for the talk. And based on my understanding, you run your diffusion model based on EVM model. And why don't you sample from EVM? Because EVM is just directly minimize the KL with data, and your diffusion model decrease KL divergence between your model and EVM models.
The question was, why don't I directly sample from EVM? Yeah, thanks for the question. So that boils down to the problem of how to sample from EVM. So yeah, what people do is to run Langevin Monte Carlo on EVM. And as we talked earlier, like this will, at least in theory, Langevin Monte Carlo will give us good samples in very long run. And also in practice, there is the sample quality is not very good if we directly sample from EVM using Langevin Monte Carlo. So I think you can think of this diffusion model is something that is trained to generate a sample from energy-based model. So another like parametric sampler that is trained to generate from energy-based model. Of course, it's an approximation, but like if we run Langevin Monte Carlo, it will be an approximation anyways.
Okay, yes, thank you.
I guess there's a question in the chat. Yeah, the question in the chat is, why is MCMC related to the normalization constant in EVM? So yeah, this is something that is well known regarding energy-based model. So energy-based model, so if you want to compute the maximum likelihood, basically the minimization of this KL divergence for energy-based model, you want to compute the gradient of energy-based model parameters. So what we eventually want to do is we want to train the parameters of this energy, but then this normalization constant is also dependent on the parameters of the energy. So we have to take the gradient for the normalization constant as well. And that, unfortunately, I don't have the expression in this set of slide deck, but if we take the gradient of this normalization constant with respect to energy model's parameter, and that leads to an expression that requires MCMC to approximate. Yeah, I mean, it's a little bit difficult to explain it without the actual equation, but yeah, that's the high level comment that I can say. Yeah, I hope this answers your question in the chat.
So is there any other question?
Thanks for the talk. So in the last work, you jointly trained the diffusion model and an energy-based model, and you accelerate the sampling process of the diffusion model by the energy-based model, right?
Yes.
Since there are many pre-trained diffusion models, so do you think we can apply these pre-trained diffusion models and we only train the energy-based model for this kind of acceleration?
By pre-trained diffusion model, you mean like pre-trained checkpoints, right?
Yes, yes. So we do not train the diffusion model, we only train the energy-based model.
Ah, I see. So first, we also use the pre-trained checkpoints. So as can be seen in the, so we also use the pre-trained checkpoints to initialize the diffusion model. But I believe, I'm afraid the simultaneous training is necessary because what we eventually want to solve is minimax problem. So it's important for both models to be optimized simultaneously.
So I guess you use the different objectives for training the diffusion model as the pre-trained one, right? Because pre-trained, they are usually trained by like denoising formation.
Yes.
Okay, thanks. Thank you.
Okay, then thank you, Sangwoong, for your great talk, and thank you, audience, for your attendance. So this is the end of today's seminar. Thank you very much.
Thank you.